Something changed on October 29th. An object from beyond our solar system, travelling through the darkness for billions of years, reached its closest point to the Sun. And in those final hours, it did something that left astronomers staring at their screens in disbelief. Its brightness exploded. Not gradually, the way comets are supposed to brighten, violently, twice as fast as any model predicted, releasing water at 40 times the rate it had been just weeks before, as if something inside had suddenly woken up. When space telescopes finally captured images, they saw something that didn't look like any comet they'd studied. No dust tail, just a strange elongated glow. And beneath the surface, James Webb detected a thick crust forged by billions of years of cosmic radiation, hiding whatever lies beneath. Harvard astrophysicist Avi Loeb has formally requested NASA release all their data on 3I Atlas, because the more we learn, the less it behaves like a simple ball of ice. So relax, let the question linger. Tonight, we're exploring what happens when something ancient comes close enough to study, and leaves us wondering if we're looking at a comet at all. The first thing you need to understand about 3I Atlas is that it wasn't supposed to do what it did. Astronomers had been tracking it for weeks as it approached the Sun, watching its brightness increase in the predictable way that comets brighten when solar radiation starts warming their frozen surfaces. Ice turns to gas, activity increases, brightness climbs. It's a process we've observed countless times, modelled with reasonable accuracy, understood through decades of study. And then, on October 29th, everything changed. Two astronomers were monitoring the comet in real time, Qisheng Jiang from Lulin Observatory in Taiwan, and Carl Battams from the US Naval Research Laboratory. They'd been tracking 3I Atlas for days, documenting its approach to perihelion, the closest point to the Sun, expecting to see the typical gradual brightening that happens when a comet reaches maximum solar heating. Instead, they watched as the brightness exploded, not gradually, not predictably. The rate of brightening suddenly doubled, as if someone had thrown a switch, as if the comet had been holding back and suddenly decided to release everything at once. They had no immediate explanation for what they were seeing. Think about that. These are professionals who've spent their careers studying comets. They understand the physics, they know what to expect. And yet the data coming in from 3I Atlas didn't match anything in their models. The brightness was increasing at twice the rate it had been just days before, and the timing, exactly at perihelion, felt too precise to be coincidence. But brightness was just the beginning. Radio observations revealed something even stranger. In the 2 weeks leading up to perihelion, 3I Atlas was losing water at an extraordinary rate, approximately 5.7 times 10 to the 28th power molecules per second. That number might not mean much on its own, but here's what matters. It was 40 times more than the comet had been losing just 1 month earlier. 40 times. Imagine a faucet dripping slowly, then suddenly being turned to full blast. Except there's no hand on the valve, no mechanism that should cause such a dramatic change. Just this ancient object from interstellar space suddenly pouring water into the void, like it had been holding it back for billions of years, and finally let go. The spectrum analysis added another layer. The light from 3I Atlas had shifted bluer than the Sun's own spectrum, indicating the presence of specific carbon molecules, C2 and amidogen compounds like NH2. These are signatures of active sublimation, the process where ice turns directly to gas. So far, this was expected. This is what comets do when they heat up near the Sun. But the rate, the timing, the sheer violence of it, none of that matched what comets from our solar system do. And here's the thing, 3I Atlas didn't form in our solar system. It came from somewhere else. Another star, another environment, different chemistry, different conditions, different everything. So why would we expect it to behave like the comets we're familiar with? Space-based telescopes turned their instruments toward the comet during this critical period. SOHO, Stereo A, and the new GOES 19 satellite all equipped with coronagraphs that can observe objects close to the Sun without being blinded by its glare. They captured images of 3I Atlas during perihelion, and what they saw didn't look like a typical comet. The comet appeared as a faint, elongated spot, stretched out, glowing, but there was something fundamentally wrong with the image. It had no dust tail. When you picture a comet, you think of that long streaming tail, the dust particles lifted off the surface by escaping gas, pushed away from the Sun by radiation pressure. It's one of the most basic features of comet behaviour. The tail always points away from the Sun. It's predictable, it's universal. Every comet does it, except 3I Atlas. What the telescopes captured was just this diffuse glow, gas emission, the signature of water vapour escaping from the nucleus, but no visible dust trail, no particles, just gas and this strange elongated form that didn't fit the pattern. Where's the dust? Some scientists proposed an explanation that almost makes sense. They suggested that initially carbon dioxide gas was escaping from the comet at a distance of about 3 astronomical units from the Sun. This CO2 would have been acting as a protective layer, cooling the surface, preventing the deeper water ice from sublimating, like a shield between the nucleus and solar radiation. But then, as the comet got closer, that CO2 layer depleted, and when it did, the water ice underneath was suddenly exposed to direct sunlight for the first time. The result? Explosive activity, violent outgassing, the dramatic surge in brightness that Jang and Batoms witnessed. It's a plausible explanation. It fits some of the observations, but it doesn't explain the precision of the timing. It doesn't explain why the transition happened exactly at perihelion, and it certainly doesn't explain the missing dust. Because comets produce dust. It's what they do. Even if they're ice-rich, there's always particulate matter mixed in. Rocky grains, silicates, organic compounds that don't vaporize easily. That material should be visible in the images, but it's not there. So either 3I Atlas has a composition so unusual that it contains almost no solid material, just pure volatile ices that turn entirely to gas, or something else is going on. Something that doesn't fit into our standard model of what a comet is. And then there's what James Webb found. The James Webb Space Telescope had been observing 3I Atlas since August, months before perihelion. Webb's near-infrared spectrograph analysed the light coming from the comet, breaking it down wavelength by wavelength, molecule by molecule, looking for clues about what this object is made of. The data confirmed that 3I Atlas is unusually rich in carbon dioxide. That part matched expectations based on earlier observations, but Webb revealed something more profound, something that changes how we have to think about this object. The outer layers of 3I Atlas have been fundamentally transformed by cosmic radiation. To understand why this matters, you need to know what happens to objects in interstellar space. In our solar system, we're protected by the heliosphere, a bubble created by the solar wind that shields us from most galactic cosmic rays. Those high-energy particles come from supernova explosions, from collisions in distant stellar systems, from violent processes scattered across the galaxy. In our protected bubble, we're mostly safe from them. But in interstellar space, there is no protection. Objects drifting between the stars are exposed to the full, unrelenting bombardment of cosmic radiation for millions of years, billions of years. Every second of every day, high-energy particles slam into the surface, penetrating deep, breaking chemical bonds, rearranging molecular structures. Roma Maggiolo, a researcher from the Royal Belgian Institute for Space Aeronomy, led a team that used computer simulations to model what happens to ice and rock after prolonged exposure to cosmic rays. They adapted models originally developed for comets in our own solar system, but extended the timescales to account for the vastly longer journeys that interstellar objects experience. The results were striking. After approximately 1 billion years of continuous radiation exposure, the transformation is complete. The outer layers of the comet are no longer what they were when the object first formed. Carbon monoxide converts to carbon dioxide. The crystalline structure of water ice changes. Chemical bonds break and reform into new configurations. The surface becomes something different. What Webb detected was a crust, a shell of radiation processed material extending roughly 50 to 65 feet into the comet's interior. A layer that has been cooked by cosmic rays for so long that it no longer represents the original composition from wherever 3I Atlas was born. Maggiolo put it bluntly. He said that 3I Atlas is now a product of its interstellar journey, rather than a pristine sample from its origin system, at least on the outside, which raises the obvious question: what's underneath? If the outer shell has been transformed by radiation, chemically altered beyond recognition, then what lies deeper in the nucleus? Is there pristine material in the core? Material that hasn't been touched by cosmic rays, that still carries the original chemistry from the star system where this object formed billions of years ago? We don't know. And here's the frustrating part: we might never know, because we don't know how thick the radiation crust really is. The simulations suggest 50 to 65 feet, but that's based on models. The actual depth could be different, and we don't know if the solar heating during perihelion was intense enough to erode through that crust and expose deeper layers. Maggiolo noted that 3I Atlas remains scientifically valuable despite this complication. If researchers can compare observations from before perihelion, when the radiation crust was intact, with observations after, when solar erosion might have stripped away outer layers, they might be able to glimpse what's underneath. They might still be able to read the chemical signature from another star system, but that's assuming the crust eroded, assuming the nucleus didn't disintegrate entirely, assuming we can detect the difference. The comet has passed perihelion now. It's moving away from the sun, heading back out toward the darkness, and through November and December of 2025, it will be visible from Earth as it continues its outbound trajectory. This is the window, the brief period when we can gather data, analyze spectra, look for changes in composition that might tell us whether the solar heating exposed anything new. But there's something else, something Zhang and Battams noted in their observations that has other astronomers paying very close attention. They said the comet's evolution after perihelion could be just as unusual as the explosive brightening that preceded it, maybe more unusual. What does that mean? If 3I Atlas were simply responding to solar heating, its behaviour should be predictable now. As it moves farther from the sun, as radiation decreases, the activity should fade. The brightness should drop. The outgassing should slow, and eventually stop. That's what normal comets do. But Zhang and Battams seem to be suggesting that 3I Atlas might not follow that pattern, that something else might happen, something they can't predict based on current understanding. And that uncertainty is what makes this moment so critical, because we're watching in real time as an object from beyond our solar system behaves in ways that challenge fundamental assumptions. An object that's travelled for billions of years through environments we can barely imagine. An object that came close enough for us to study and then did something that doesn't fit our models. At perihelion, 3I Atlas reached a visual magnitude of approximately 9, bright enough to be visible through a small amateur telescope, if you knew exactly where to look, and if you could observe it without the sun's glare overwhelming everything. But here's the problem: during those critical hours, 3I Atlas was positioned so close to the sun, in our sky, that ground-based observation was nearly impossible. We had to rely on space-based coronagraphs, instruments specifically designed to block out the sun's light, so we can see what's happening in the region immediately around it. And what those instruments captured was an object that looked nothing like what we expected. The images showed this elongated, glowing form, gas emission, the hydroxyl signature of water vapour streaming away from the nucleus, but still no visible dust, no particles, just this strange, diffuse glow that shouldn't exist on its own. And beneath all of this, beneath the observations and the models and the careful scientific language, there's a question that keeps surfacing. A question that most researchers won't ask directly, but that hangs in the background of every discussion about 3I Atlas. What if we're not looking at a simple comet? What if the composition, the structure, the behaviour, all of it, is fundamentally different from anything we've encountered before? Not just because it formed around a different star, but because it's something we don't have a category for yet. The trajectory alone is unusual. 3i Atlas is moving at over 130,000 miles per hour relative to our solar system. It's travelling in what observers describe as an unusually flat, straight path. Not the curved, chaotic trajectory shaped by billions of years of gravitational interactions with planets and passing stars. This is a trajectory that says, I came from somewhere else and I'm passing through. Some estimates suggest 3i Atlas could be 7 to 12 billion years old, 3 billion years older than our Sun, older than Earth, older than any planet in our solar system. This object has been travelling through the galaxy since a time when the Milky Way itself looked different. What has it seen? What stellar systems did it pass near? What radiation environments did it traverse? We don't know where it formed. We don't know what happened to the star it once orbited. We don't know if that star still exists or if it died billions of years ago, scattering its planetary system into the void. All we know is that 3i Atlas survived. It travelled through the darkness for longer than our world has existed, and now it's here, for this brief window, close enough to study, close enough to question, and the more we look, the stranger it gets. There's a detail about 3i Atlas that doesn't get enough attention, but it should, a detail that changes the entire context of what we're looking at. This object might be older than our solar system, not by a little, by billions of years. Age estimates for 3i Atlas range from 7 to 12 billion years. To put that in perspective, our Sun is about 4.6 billion years old. Earth is roughly the same age. Everything in our solar system, every planet, every moon, every asteroid and comet, formed from the same disk of gas and dust that collapsed to create the Sun. Nothing here is older than 4.6 billion years. But 3i Atlas could be 3 billion years older than that. It could have formed when the Milky Way was a younger, more violent place, when the galaxy was still in its early stages of evolution, populated by massive stars that lived fast and died young, seeding the interstellar medium with heavy elements through supernova explosions. That's the environment this object might have been born in. Not the relatively calm, metal-rich region where our Sun eventually formed, but somewhere more chaotic, more ancient, the thick disk of the galaxy, where the oldest stars cluster. And if that's true, then the chemistry inside 3i Atlas, assuming anything pristine remains beneath the radiation crust, could be fundamentally different from anything we've ever studied. Different ratios of elements, different isotopes, different organic compounds formed under conditions that no longer exist anywhere in the galaxy. This is why the radiation crust is so frustrating. It's like finding an ancient text and discovering that the outer pages have been weathered beyond recognition. You know there's information underneath, but you can't read it. You can only see what time and exposure have done to the surface. Roma Maggiolo's simulations showed that cosmic rays penetrate deep into the comet's structure, 50 to 65 feet, according to the models. That's not just surface damage, that's a shell. A layer thick enough to completely obscure whatever lies beneath. And here's what makes it worse. We don't know if that entire shell was stripped away during perihelion, or if only a thin outer layer eroded. Solar heating is intense close to the Sun. The radiation, the thermal stress, the tidal forces, all of it works to tear material off a comet's surface. But how much was removed from 3i Atlas? A few inches? A few feet? Enough to expose pristine material? Or just enough to reveal more radiation process crust underneath? The only way to know is to compare the spectroscopic data from before perihelion with observations taken now as the comet moves away. If the chemical signature has changed, if new compounds appear, if isotope ratios shift, that would suggest deeper layers have been exposed. But if the spectrum looks the same, if the composition appears unchanged, that could mean one of two things. Either the crust is thicker than expected, and solar erosion didn't penetrate deep enough, or the entire nucleus has been transformed all the way through and there's no pristine material left to find. Both possibilities are disappointing for different reasons. There's another angle to this that researchers like Susanne Fausner have been exploring. She's a professor at Forschungszentrum Jülich in Germany, and she's proposed something that reframes what interstellar objects like 3i Atlas actually represent. She suggests they might not just be cosmic debris, they might be the seeds of planets, Her computer models show that young stars, surrounded by their planet-forming disks of gas and dust, could capture millions of interstellar objects as they drift through the galaxy. And once captured, these objects, already hundreds of meters, or even kilometers in size, could serve as the nucleus around which planets grow. This solves a long-standing problem in planetary science. We know planets form through accretion, where small particles stick together to gradually build larger objects. But there's a gap in our understanding. Simulations show that once objects reach about a meter in size, the chaotic environment of a protoplanetary disk should cause them to collide and shatter rather than continue growing. So how do you get from meter-sized rocks to planet-sized worlds? Felsner's answer: you don't start from meter-sized rocks. You start from interstellar objects that are already large enough to gravitationally attract material and begin the planet-building process. The galaxy delivers ready-made seeds, and young star systems capture them. Her models suggest this process works especially well around massive stars larger than our Sun, which would explain why gas giant planets like Jupiter are more commonly found around such stars, even though their planet-forming disks only last about 2 million years. Too short a time for traditional planet formation theories to work. If Felsner is right, then 3I Atlas isn't just an ancient comet. It's the kind of object that could have become a planet if it had been captured by a young star billions of years ago, a building block of worlds that never got built. A planetary seed that drifted through the galaxy for eons without finding a home. And that changes how you look at it. This isn't just frozen debris. It's potential, unrealized possibility, the raw material of creation that never got the chance to create. But let's return to what's happening right now, because the story of 3I Atlas isn't over. It's entered what might be the most revealing phase. The comet has passed perihelion. It's moving away from the Sun now, heading back out into the solar system and eventually into interstellar space. And as it does, astronomers around the world are watching it carefully, because this is when things could get even stranger. Zhang and Battams were explicit about this in their observations. They noted that the post-perihelion evolution of 3I Atlas could be just as unusual as the explosive brightening that preceded it. They weren't being vague. They were suggesting that the comet's behaviour might not follow predictable patterns even now. Why would they say that? For a normal comet, the answer is simple. Once it passes perihelion and starts moving away from the Sun, activity decreases. Solar radiation weakens with distance. The heating drops. Sublimation slows. Brightness fades. It's a gradual decline that mirrors the gradual increase on the way in. But if 3I Atlas doesn't follow that pattern, if the brightness stays high or increases or shows periodic variations that don't correlate with solar distance, that would suggest something else is driving the activity. Something internal, something that has nothing to do with external heating. And that would be a problem for the comet hypothesis. There's a concept in planetary science called outgassing lag. Sometimes comets retain heat in their interiors even as they move away from the Sun. That trapped thermal energy can continue driving sublimation for a while, causing delayed outbursts. It's well documented. It happens. But there's a limit. The effect fades relatively quickly as the comet cools. If 3I Atlas shows sustained activity weeks or months after perihelion, activity that can't be explained by residual heat, then we'd have to consider other explanations. What kind of explanations? Radioactive decay is one possibility. If the nucleus contains enough radioactive isotopes, elements like aluminum-26 or iron-60 that generate heat as they decay, that could provide an internal energy source independent of solar heating. It's rare, but not impossible, especially for an object that might have formed in a supernova-enriched environment billions of years ago. Another possibility is tidal heating. As 3I Atlas passed close to the Sun, tidal forces would have flexed the nucleus, generating friction and heat in the interior. That heat could continue driving activity even as the comet moves away. But again, there are limits. Tidal heating should fade relatively quickly once the object is no longer under extreme gravitational stress. And then there's the possibility that no one wants to say out loud. but that keeps appearing in the margins of scientific discussions. What if the activity is controlled? What if there's some kind of threshold mechanism inside the nucleus that triggers at specific conditions, distance from a star, radiation levels, temperature, and continues operating according to internal programming rather than passive physical processes? Before you dismiss that as science fiction, consider what we already do with our own spacecraft. We build probes that activate at specific times, that wake up when they detect certain environmental conditions, that follow pre-programmed sequences triggered by external stimuli. The concept isn't exotic, the question is whether there's any evidence that 3i Atlas is doing something similar. And that's where Avi Loeb enters the conversation. Professor Abraham Loeb, former chair of Harvard's astronomy department, has been one of the most vocal scientists calling for rigorous investigation of interstellar objects. He was the leading voice arguing that Oumuamua, the first confirmed interstellar visitor in 2017, deserved serious scientific scrutiny rather than rushed explanations. Oumuamua was strange. It had an elongated shape unlike anything in our solar system. It accelerated as it left, moving faster than gravity alone could explain, and it showed no signs of typical comet activity, no tail, no coma, no outgassing that could account for the acceleration. Loeb proposed that Oumuamua might be a light sail, a thin, reflective surface pushed by solar radiation. The kind of technology we're already developing for our own interstellar missions, the acceleration, the shape, the lack of cometary activity, all of it fit that hypothesis better than the natural explanations being offered. Most astronomers disagreed. They argued that Oumuamua was probably just an unusual comet, or an asteroid fragment, or some natural object we hadn't encountered before. Loeb's suggestion of artificial origin was considered too speculative, too extraordinary, not worth serious consideration without extraordinary evidence. But Loeb's point wasn't that Oumuamua was definitely artificial. His point was that we shouldn't dismiss the possibility without thoroughly investigating it, that science requires following evidence wherever it leads, even if it leads to uncomfortable conclusions. Now, with 3i Atlas, Loeb has formally requested that NASA release all scientific data to the broader research community and the public. Not just summary findings, not just press release friendly highlights, all of it. The raw observations from Swift, from SOHO, from Stereo, from GOES 19, the spectroscopic data from Webb, the trajectory measurements, everything. His argument is straightforward. This is only the third confirmed interstellar object ever detected passing through our solar system. The data collected represents humanity's best chance to understand what these objects are really like. That information shouldn't be restricted. It should be available for independent analysis by researchers around the world. But there's an unspoken question beneath Loeb's request. What exactly is in that data? What has NASA observed that hasn't been publicly discussed? Are there measurements, patterns, anomalies that don't fit easily into preliminary papers and press conferences? The scientific community is divided on how to interpret 3i Atlas. Some researchers are comfortable saying it's simply a comet with unusual composition, modified by cosmic radiation, behaving in unexpected ways because we've never studied an interstellar comet this closely before. They point to the carbon dioxide, the water vapour, the molecular signatures that all indicate this is a natural object. Just a weird one. But others are less certain. They point to the explosive brightening that doesn't match models, the missing dust tail, the precise timing of the outburst at perihelion, the flat, fast trajectory, the possibility that its internal structure is fundamentally different from anything in our local cosmic neighbourhood. And they ask, quietly, in research papers and conference presentations, what else could explain these observations? No one is saying it directly. No one wants to be the scientist who jumps to conclusions without sufficient evidence. But the questions are there, hanging in the air. What if 3i Atlas isn't entirely natural? What if there's something about its composition, its structure, its behaviour that suggests it's more than just a ball of ice and rock that's been drifting through space for billions of years? The problem is that we have no framework for answering that question. Our entire scientific understanding of comets, asteroids, and interstellar objects is based on natural formation processes. We look at spectra, see carbon dioxide and water, and think comet. We see an elongated shape and think fragment from a planetary collision. We calculate trajectories based on gravitational interactions with stellar systems. But what if some of the signatures we're trained to interpret have multiple possible explanations? What if things that look natural could also be consistent with designed objects? How would we even know the difference? This isn't about declaring 3i Atlas is artificial. This is about acknowledging that our sample size for interstellar objects is exactly 3. Oumuamua, Borisov, and now 3i Atlas. 3 objects out of the potentially billions or trillions drifting through the galaxy. We're drawing conclusions about an entire class of phenomena based on 3 examples, and each of those 3 has surprised us. Oumuamua accelerated in ways that couldn't be fully explained by outgassing. Borisov was relatively normal, but came from a completely different stellar environment with distinct chemical signatures. And now 3i Atlas is brightening explosively, losing water at unprecedented rates and challenging our understanding of how radiation-processed comets should behave. Maybe all 3 are natural objects with unusual properties. Maybe the universe is more diverse than we've given it credit for, and every interstellar visitor will teach us something new about the variety of formation processes across the galaxy. That's probably the right answer, the simplest explanation, and it's almost certainly correct, but the explosive brightening keeps nagging at researchers, the timing of it, the way it happened exactly at perihelion, the sudden surge that doubled the rate of change without warning, because there's a difference between unusual but explainable, and unusual in a way that suggests something we haven't considered. And as 3i Atlas moves away from the Sun, as we continue gathering data through November and December, we might finally figure out which category this object belongs to, or we might just end up with more questions. One of the details about 3i Atlas that keeps coming up in scientific discussions, but hasn't made it into most public coverage, is the mass. Early estimates suggest this object has a mass of approximately 33 billion tons. That's enormous for a comet. Most comets we observe from our own solar system are much smaller. Halley's comet, one of the most famous in human history, has an estimated mass of around 22 billion tons. So 3i Atlas is significantly more massive than Halley, perhaps 50% larger. Now, mass alone doesn't necessarily mean anything unusual. Larger objects exist throughout the solar system, but combined with everything else, the velocity, the explosive outgassing, the unusual trajectory, the missing dust, it adds another data point to a growing list of characteristics that make this object stand out. And then there's what that mass implies about structural integrity. For an object to hold together while losing water at 40 times its normal rate, while experiencing the intense thermal stress of perihelion, while being bombarded by solar radiation and buffeted by solar wind, it has to be solid, dense, structurally coherent in ways that loose rubble piles are not. Most comets are what scientists call rubble piles. They're not solid chunks of ice and rock. They're loose aggregations of smaller pieces, held together weakly by gravity and frozen volatiles. When these objects heat up, when internal pressure builds from sublimating ice, they often fall apart. The structure can't handle the stress. We've seen this happen repeatedly. Comet Shoemaker Levy 9 broke into more than 20 fragments before it crashed into Jupiter in 1994. Comet Linear disintegrated into a cloud of debris in 2000. Comet Ison fell apart as it rounded the Sun in 2013. It's a common fate for comets that get too close to extreme conditions. 3i Atlas should have disintegrated. The violence of its outburst, the rate of mass loss, the thermal stress, all of it pointed towards structural failure. Astronomers were watching for it, waiting for the telltale signs, the nucleus splitting, the brightness fragmenting into multiple peaks, the characteristic pattern of a comet coming apart. It never happened. 3i Atlas held together through perihelion. It survived forces that should have torn it apart, and that suggests something about its internal structure, something that doesn't match the typical rubble pile model. Maybe the radiation crust acted as a shell, a protective layer hardened by billions of years of cosmic ray bombardment, holding the interior together like armor. That's one possibility. The simulations suggest the crust extends 50 to 65 feet deep. thick enough to provide structural support, hard enough to resist the pressures that would shatter a more loosely bound object. But there's another possibility, one that's harder to discuss in scientific terms, because it ventures into territory where data becomes sparse and speculation begins. What if the nucleus is intentionally reinforced? What if the internal structure isn't the result of random accretion, but deliberate design? If you were engineering a probe to survive billions of years travelling through interstellar space, what would you need? Protection from radiation. Check, the crust provides that. Structural integrity to withstand micrometeorite impacts and gravitational stresses. Check, high mass and density provide that. A design that could handle extreme temperature variations without active systems. Check, natural materials could serve that function. And you'd want it to be mostly passive, not requiring continuous power or maintenance, dormant for the vast majority of the journey, only activating when it encountered specific trigger conditions. Like proximity to a star, this is where the speculation becomes uncomfortable for most scientists, because once you start describing characteristics that would also be consistent with artificial objects, you're leaving the realm of what can be easily tested and entering the realm of what-ifs and maybes. But here's the thing, the question isn't whether such an object is possible. We know it's possible. We're already planning missions that would do exactly this. Breakthrough Starshot, for example, proposes sending tiny light sail probes to nearby star systems. Those probes would be designed to survive decades or centuries in transit, activate upon arrival, gather data, and potentially transmit it back to Earth. The question is whether there's any evidence that 3i Atlas is doing something similar. And the honest answer is, we don't have enough data to rule it out. That's not the same as saying it's likely. It's not the same as claiming we've found proof of artificial origin. It's simply acknowledging that with 3 interstellar objects observed out of potentially trillions that exist, we can't yet say with certainty what the full range of possibilities includes. The 2 Mars rovers, Curiosity and Perseverance, had a unique opportunity to observe 3i Atlas from their vantage point on the Martian surface. Different angle, different perspective. The kind of observations that could reveal details invisible from Earth. The data from those observations hasn't been fully released yet. We don't know what they saw. We don't know if their instruments picked up anything that Earth-based telescopes missed. And that brings us back to Loeb's call for transparency, because the more eyes on the data, the better chance we have of understanding what's really happening. Maybe one research group will notice something another missed. Maybe an independent analysis will reveal a pattern that changes the interpretation entirely. Science works best when it's open, when data is shared, when unusual observations are met with rigorous analysis, rather than premature dismissal or premature acceptance. There's also the question of what happened during those critical days when 3i Atlas was behind the Sun. The period when it was closest to the Sun, under maximum stress, potentially undergoing its most dramatic changes, and completely unobservable from Earth. Solar conjunction, the astronomical term for when an object passes too close to the Sun to observe from our perspective. For several days, 3i Atlas was lost in the glare. No ground-based telescope could see it. Even space-based instruments had limited views. For most objects, this is just an inconvenience, a frustrating gap in the data, but for 3i Atlas, it was the most critical period of its entire journey through our solar system. The moment when everything should have been visible, when the maximum activity, the peak brightness, the most revealing behaviour would occur. And we were blind. Some have noted that the timing feels almost too convenient. Natural processes don't usually care about human observation schedules. But here was an object that held together through weeks of increasing activity, behaved strangely enough to raise questions, and then pass through its most critical phase while hidden from view. It's probably just bad luck, just unfortunate geometry. The universe doesn't arrange itself for our convenience, and there's no reason to think 3i Atlas's trajectory was anything other than the natural result of gravitational interactions over billions of years. But it's worth noting that if you wanted to perform a close stellar flyby, to gather data, to execute a gravitational assist maneuver, to accomplish some mission objective, the ideal time would be when you're not being observed, when the star you're approaching blocks the view from any nearby planetary systems. Again, this isn't evidence of anything. It's just an observation about timing, about how things lined up, about the gap in our data that happens to coincide with the most revealing moment. NASA's stereo mission captured images showing 3I Atlas interacting with the solar wind during perihelion. Those images revealed structures in the coma, asymmetries in the gas distribution, patterns suggesting complex dynamics at play. But interpreting those images requires understanding not just cometary physics, but plasma physics, magnetohydrodynamics, and the chaotic environment near the Sun. The interaction between the comet's outgassing and the stream of charged particles flowing from the Sun creates effects we can observe. Magnetic field distortions, particle acceleration, plasma instabilities. Those effects can tell us about the composition and structure of the comet in ways that simple spectroscopy cannot. But they're also complicated, difficult to model, open to multiple interpretations, and that data, those images, those measurements of magnetic field interactions, those observations of how 3I Atlas responded to the solar wind environment, that's part of what Loeb wants released, because hidden in that complexity might be signatures that distinguish between different hypotheses about what this object really is. There's a pattern emerging in how we handle interstellar visitors. We detect them, we observe them as best we can with existing instruments, we gather data, and then they leave before we can do anything more comprehensive. Oumuamua passed through in 2017, moving so fast that by the time we realised what it was already on its way out. We got glimpses, measurements, enough to know it was unusual, not enough to understand it fully. Borisov, in 2019, gave us more time. It was clearly a comet, tail, coma, all the expected features. But its chemistry was different. Its carbon monoxide ratio was unlike anything in our solar system. It came from a different stellar environment, and you could see that in the spectroscopic signatures. Now 3I Atlas. More massive than the others, more active, more challenging to interpret. And like the previous two, it's just passing through. A brief visitor that will disappear back into interstellar space, carrying its secrets with it. We need to get better at this. We need missions ready to launch on short notice when these objects are detected. Probes that can intercept them, fly alongside them, take close-up images, sample their composition directly. That's what ESA's Comet Interceptor mission is designed to do. It won't target a specific object. Instead, it will wait in space at a gravitationally stable point, a Lagrange point, ready to chase down whatever interesting comet or interstellar object appears next. The goal is to reach it early, while it's still pristine, before solar heating has altered the surface chemistry. If we had that capability now, if we could send a probe to 3I Atlas, what would we find? What would close-up images of the nucleus reveal? Would we see the radiation crust? Would we find evidence of internal structure? Would the surface show features that match natural accretion processes? Or something else? We'll never know. At least not with this object. By the time any mission could be designed, approved, built and launched, 3I Atlas will be long gone. But the questions it's raising will shape future missions. The anomalies it's displaying will guide what instruments we build, what measurements we prioritize, what hypotheses we test, because every interstellar visitor teaches us something, even if what it teaches us is how much we don't know. There's a concept in science called the principle of mediocrity, the idea that Earth, our solar system, our galaxy, none of it is special. We're not at the center of anything. We're not unique. We're typical examples of what exists throughout the universe. That principle has served us well. It's led to discoveries of exoplanets, of organic molecules in space, of conditions suitable for life scattered across the galaxy. It's taught us that the ingredients for life are common, that planetary systems are the norm rather than the exception. But mediocrity has limits, because if everything is typical, if nothing stands out, then we'd never encounter anything. That challenges our understanding. We'd never find objects that don't fit our models. We'd never have to revise our theories or expand our categories. 3I Atlas stands out. It's not typical. It's not behaving the way interstellar comets are supposed to behave, assuming we even know what supposed to means when we've only seen 3 of them, and that's valuable, not because it proves anything extraordinary, but because it forces us to think harder, to question assumptions, to acknowledge that the universe is more complex, more diverse, more full of surprises than our current understanding accommodates. Maybe 3I Atlas is just a really unusual comet, an outlier, a statistical anomaly that happens to combine several rare characteristics in one object. The explosive brightening, the missing dust, the high mass, the ancient origin, maybe all of that is just the result of unlikely but natural circumstances. Or maybe it's telling us something more profound, that our categories are too narrow, that comet and asteroid don't capture the full range of what exists in interstellar space, that we need new frameworks, new ways of thinking about objects that have survived billions of years travelling between stars. Either way, we won't figure it out by dismissing the anomalies. We won't learn by assuming everything must fit into boxes we've already built. We learn by following the data, by staying open to possibilities, by testing hypotheses rigorously regardless of how comfortable or uncomfortable they make us. That's what Loeb has been arguing for. Not that every unusual object is artificial, but that artificial origins should be a hypothesis we're willing to test, rather than a possibility we rule out by assumption. And right now, 3I Atlas is still out there, still visible, still releasing gas, still showing activity, still available for observation. The next few weeks will tell us whether its behaviour continues to deviate from predictions, or whether it settles into patterns we can explain through natural processes. The spectroscopic data will tell us whether solar erosion exposed deeper layers, or whether the radiation crust remained intact. The trajectory data will tell us whether there are any unexplained accelerations, any course corrections that can't be accounted for by outgassing in directions we can observe. And all of that information, all of those observations, all of that data will eventually make it into scientific papers, conferences, databases. But the question is whether it will be enough. Whether the data we can gather from Earth, from current satellites, from instruments that weren't designed specifically for interstellar objects, whether all of that will be sufficient to answer the questions 3I Atlas has raised, or whether we'll be left once again with fragments of understanding, pieces of a puzzle that don't quite fit together, anomalies that resist easy explanation, and the nagging sense that we're missing something important, something hidden in plain sight, something that would make sense if only we could see it from the right angle, with the right instruments at the right time. 3I Atlas came from the darkness. It blazed bright for a moment, and soon it will return to the darkness, carrying whatever secrets it holds back into the endless night between stars. What it leaves behind is questions, important questions, questions that deserve answers. There's a detail about the explosive brightening that hasn't been discussed much outside technical papers, but it's worth paying attention to: the timing. The brightness surge didn't happen gradually as 3I Atlas approached the Sun. It didn't increase steadily over weeks in proportion to solar heating. It jumped, suddenly, at a very specific moment, right at perihelion, when the comet was at its absolute closest point to the Sun. That precision is unusual. Natural processes tend to be messy, gradual. When ice heats up and turns to gas, the transition happens over time as temperature increases. You'd expect to see a smooth curve, a predictable acceleration in brightness that matches the increase in solar radiation. What Zhang and Battams observed was more like a step function, normal brightening, then suddenly twice the rate, as if something switched on. The scientific explanation for this is threshold effects, the idea that sublimation doesn't increase linearly with temperature. Instead, there are critical points where the rate jumps dramatically. When ice reaches a certain temperature, when pressure builds to a certain level, when protective layers deplete suddenly rather than gradually, the system can shift from one state to another almost instantaneously. That's plausible. It fits known physics. Systems can have tipping points where small changes in conditions produce large changes in behaviour, but threshold effects are usually predictable. If you know the composition, the structure, the thermal properties of an object, you can model where those thresholds should occur. You can predict, within a reasonable margin, when a comet should start brightening dramatically. The models for 3I Atlas didn't predict what happened. The brightening exceeded expectations, the timing was more precise than anticipated, and the rate of water loss, 40 times higher than just weeks before, suggests something beyond simple thermal physics. Maybe the models were incomplete. Maybe we don't understand the radiation process crust well enough to predict how it would behave under extreme heating. Maybe the internal structure of 3I Atlas is so different from typical comets that our standard assumptions don't apply. Or maybe there's something else going on. In engineering, threshold-triggered systems are common. You design something to activate at a specific condition. A thermostat that turns on heating when temperature drops below a set point. A pressure valve that opens when force exceeds a threshold. A timer that triggers an event after a certain duration. These systems are everywhere in our technology because they're useful. They allow complex behaviors to emerge from simple triggers. You don't need continuous control. You just need to detect when conditions are right and respond accordingly. If you were designing a probe to operate in interstellar space, to remain dormant for billions of years, and only activate when approaching a star, a threshold-triggered system would be ideal. No power consumption during the long journey, no risk of systems degrading over time, just a simple mechanism that responds to environmental conditions, temperature, radiation levels, proximity to a stellar gravity well. And from the outside, such a system might look very similar to natural threshold effects in cometary sublimation. It would be difficult to distinguish between designed activation and physical tipping points without detailed knowledge of internal structure. This is the uncomfortable space where speculation meets possibility, where the question "what if" becomes harder to dismiss simply because we don't have enough data to answer it definitively. The Swift ultraviolet telescope detected hydroxyl emission from 3I Atlas. That's the signature of water molecules breaking apart under solar radiation, releasing hydrogen and oxygen. It's exactly what you'd expect from a comet. It's one of the clearest indicators that water ice is sublimating from the nucleus. But hydroxyl emission doesn't tell you why the water is sublimating. It doesn't tell you whether the process is purely passive, ice heating up and turning to gas, or whether something is actively driving the release. Pumping water out rather than just letting it evaporate. The distinction matters, because passive sublimation follows predictable patterns. Active release could follow programmed sequences, and from spectroscopic observations alone, they might look very similar. There's also the trajectory to consider, not just the path 3I Atlas is following, but the implications of that path. The comet is travelling at over 130,000 miles per hour relative to our solar system. That's fast enough to have reached us from another star system in a reasonable time frame, millions of years rather than billions. Fast enough to be on a true interstellar trajectory rather than something that's been wandering the galaxy randomly for eons. And the path itself is remarkably straight, not curved, not showing the gravitational perturbations you'd expect from an object that's been passing near other stellar systems over billions of years. Just this clean, direct trajectory through our solar system and back out again. Could be coincidence, could be that 3I Atlas somehow avoided close encounters with other stars during its journey. Could be that its path was only recently deflected toward us by some gravitational interaction we can't trace. Or it could mean the trajectory is more recent than we think. That 3I Atlas hasn't actually been wandering for billions of years. That it's much younger than the radiation crust suggests. Or that it was sent on this path deliberately rather than drifting randomly. The radiation crust complicates everything, because if cosmic ray bombardment really does create a 50-65 foot thick shell of altered chemistry after a billion years, then any object that's been in interstellar space for that long would have one. Natural or artificial. It wouldn't matter, the crust would form either way, hiding whatever's underneath, making it nearly impossible to determine original composition or structure just by looking at the surface. Which means the crust isn't a problem, it's camouflage. Not intentional camouflage, necessarily. Just a natural consequence of spending enormous amounts of time in deep space. But the effect is the same. You can't see what you're really looking at, you can only see what billions of years of radiation exposure have created. And that raises an interesting possibility. If you wanted to send probes between star systems, if you wanted them to blend in with natural objects, you wouldn't need elaborate disguises. You'd just need patience. Launch them on long, slow trajectories. Let interstellar radiation do the work of creating a natural-looking surface. By the time they reach their destinations, they'd be indistinguishable from ancient comets that formed naturally. Again, this is speculation, but it's worth thinking through. Because if we're serious about searching for evidence of other technological civilizations, we need to think about what that evidence might actually look like. And it might not look like the obvious metallic spacecraft from science fiction. It might look like rocks, like ice, like objects we'd classify as natural unless we looked very, very closely. The data NASA has collected on 3i Atlas includes more than just images and spectra. There are measurements of how the comet interacted with the solar wind, how its coma responded to charged particles streaming from the sun, how the magnetic field around it behaved. Those interactions create patterns, signatures that depend on the comet's composition, its internal structure, how material is being released from the nucleus. A dense solid object would interact with solar wind differently than a loose rubble pile. An object releasing gas symmetrically would create different patterns than one with jets erupting from specific locations. And an object with internal power sources, with active systems managing material release, might create patterns that don't quite match purely passive processes. That's what Loeb wants examined. Not just the pretty pictures, not just the basic spectroscopy, but the detailed interaction data. The subtle signatures that might reveal whether 3i Atlas is responding to its environment in expected ways, or showing behaviours that suggest something more complex. This isn't about jumping to conclusions. It's about being thorough, about checking all the possibilities before settling on an explanation, about making sure we're not missing something important because we assumed we already knew what we were looking at. There's a broader context worth considering. We're at a unique moment in human history. For the first time, we have the technology to detect interstellar objects passing through our solar system. For the first time, we can study them in detail, take spectra, track trajectories, analyze composition. Before the Pan-STARRS survey came online, before we had networks of automated telescopes scanning the sky every night, these objects passed through unnoticed. They came and went in darkness, never detected, never studied. Now we see them, and what we're learning is that they're not rare. Estimates suggest there could be several interstellar objects passing through the inner solar system at any given time. Most too small or too dark to detect. But they're there, moving through the space between planets, invisible passengers on journeys that span light years. Out of all those objects, we've confirmed three that we've tracked long enough to verify their interstellar origin, 3 that we've studied enough to characterize even partially. That's a tiny sample, statistically meaningless for drawing broad conclusions, but it's what we have. And if all 3 show unusual characteristics, Oumuamua's unexplained acceleration, Borisov's distinct chemistry, 3i Atlas's explosive brightening, then maybe unusual is normal for interstellar objects. Maybe we need to revise our expectations entirely. Or maybe 3 unusual objects in a row is telling us something, that we should be looking more carefully, questioning more deeply, considering possibilities we might otherwise dismiss. The Mars rover's observations of 3i Atlas still haven't been fully analysed. We know they pointed their cameras at the comet. We know they collected data, but the results haven't been integrated into the public discussion yet. What did they see from Mars? Did the different viewing angle reveal structures invisible from Earth? Did their instruments pick up emissions at wavelengths that Earth-based telescopes missed? Mars was actually well positioned during 3i Atlas's perihelion passage. Not as close as Earth, but with a clearer view in some ways, less atmospheric interference, different geometric alignment, the kind of complementary perspective that could reveal details that single viewpoint observations miss. The fact that we haven't heard much about those observations might not mean anything. Data analysis takes time. Integration with other datasets requires careful work. It's possible the Mars observations simply confirmed what Earth-based instruments already detected. Or it's possible they found something that complicates the picture even more, something that doesn't fit neatly into current interpretations. something that needs more analysis before it can be discussed publicly. Either way, that data is part of what needs to be released, part of the complete picture that would allow independent researchers to draw their own conclusions. Because right now, what we have is fragments. Pieces of observation from different instruments, different vantage points, different times during 3i Atlas's passage. Each piece shows something interesting, but without seeing how they all fit together, without access to the complete dataset, it's impossible to say with confidence what the whole picture looks like. That's the frustration. Not that NASA is hiding evidence of aliens, but that the data exists, sitting in archives, analysed by small teams, released piecemeal through papers and press releases, while the object itself is moving away, while the window for observation is closing, while independent researchers who might see patterns others missed don't have access to the raw material they need. Transparency in science isn't about proving conspiracies wrong. It's about making sure we're using all the tools at our disposal, all the eyes that could look at data, all the perspectives that might see what others missed. If 3i Atlas is just an unusual but natural comet, thorough analysis by multiple independent teams would confirm that, would strengthen our understanding, would help us develop better models for future interstellar visitors. And if it's something else, if there are signatures in that data that don't fit natural processes as easily as we'd like, we need to know that too. Not because it would prove anything extraordinary, but because it would tell us where to focus future investigations, what questions to ask, what instruments to build, what observations to prioritize when the next visitor arrives. The universe is full of surprises, we know this. Every generation of astronomers discovers phenomena that previous generations couldn't have imagined. Pulsars, quasars, exoplanets, gravitational waves, dark energy. The list of things we didn't know existed until we developed the tools to detect them is long and humbling. Maybe interstellar objects will be the next surprise, not in the sense of discovering they exist, we knew they must exist theoretically, but in understanding what they really are, what variety they encompass, what they can teach us about stellar environments we'll never visit directly. Or maybe the surprise is already here, maybe we're looking at it right now. Maybe 3i Atlas is trying to tell us something through its behaviour, its composition, its inexplicable brightening at exactly the right moment. Maybe we're just not listening carefully enough yet. As November moves into December, 3i Atlas continues its journey outward, away from the sun, back toward the darkness it came from, and astronomers continue watching, collecting data, analysing every wavelength of light the comet emits. This is the critical period, the time when we'll learn whether the explosive brightening was a one-time event tied specifically to perihelion, or whether the comet's behaviour will continue to surprise us. If 3i Atlas fades predictably now, if its activity decreases in proportion to solar distance, if the spectrum remains consistent with what we observed before, then we'll have a stronger case for natural processes. Unusual processes, certainly. Processes we don't fully understand yet, but natural. If the brightness stays high, if activity continues or even increases, if the spectrum changes in ways that suggest deeper layers have been exposed, or in ways that can't be explained by simple erosion, then we'll have more questions than answers. And that's okay. Questions are how we learn. Questions are what drive science forward. The goal isn't to immediately explain everything. The goal is to gather data carefully, analyse it rigorously, and follow where it leads. What we know for certain is that 3i Atlas has already taught us something important. It's shown us that interstellar objects can be far more complex than we assumed, that billions of years travelling through space fundamentally transforms these objects in ways we're only beginning to understand, that radiation crusts, cosmic ray bombardment, and the harsh environment between stars create surfaces that hide as much as they reveal. It's reminded us that our models are built on limited data, that 3 confirmed interstellar visitors isn't enough to establish what normal looks like, that every new object we detect will likely challenge our assumptions in different ways. And it's forced us to ask uncomfortable questions about how we distinguish between natural and designed objects, about what evidence would actually be diagnostic, about whether we're prepared as a scientific community to recognize something truly unusual if we encounter it. These aren't just abstract philosophical questions. They're practical concerns that will shape how we approach future observations, what instruments we build, what missions we plan, what data we prioritize collecting when time is limited and opportunities are fleeting. Because here's the reality: 3i Atlas will be gone soon. Within months, it will fade beyond the reach of even our most powerful telescopes. It will return to interstellar space, continuing a journey that might last another billion years. Or it might end tomorrow if it collides with something in the darkness. We'll never know. What we're left with is the data we've already collected and whatever we can gather in these final weeks. That data will be analysed for years. Papers will be written. Models will be refined. Debates will continue in conference halls and academic journals. But the object itself, the actual comet with all its mysteries and anomalies, will be beyond reach. A memory, a data set, a series of questions that may never be fully answered. That's the nature of interstellar visitors. They don't stay. They don't wait for us to figure them out. They pass through on trajectories shaped by forces and events we can barely trace, and then they're gone. Which makes every observation precious, every spectrum worth analysing carefully, every anomaly worth taking seriously rather than dismissing because it doesn't fit expectations. There's something poetic about objects like 3i Atlas, ancient travellers carrying histories written in chemistry and structure, messengers from environments we'll never directly observe, windows into stellar systems that might not even exist anymore, into eras of galactic evolution we can only study through proxies like this. Even if 3i Atlas is entirely natural, just an unusual comet shaped by extreme conditions, it's still extraordinary, still valuable, still worth every hour of telescope time, every line of code written to analyse its spectrum, every paper debating what its behaviour means. Because it's teaching us, forcing us to expand our understanding, showing us that the universe is more complex, more diverse, more full of edge cases and outliers than our neat categories allow for. And if it's something else, if there's even a small chance that some of the anomalies point towards something we haven't considered, then we owe it to ourselves to look carefully, to check thoroughly, to follow the data wherever it leads, even if it leads somewhere uncomfortable. Avi Loeb's call for data transparency isn't about proving a hypothesis. It's about making sure we're doing science correctly, making sure we're not missing something important because assumptions closed off avenues of investigation before they were properly explored. The data exists, the observations have been made, NASA's instruments have collected an enormous amount of information about 3i Atlas, more than any previous interstellar object. That information should be available, should be scrutinized by multiple independent teams, should be tested against different hypotheses, not because any single hypothesis is more likely than others, but because that's how science works best, through open data, through independent verification, through the collision of different perspectives and approaches that sometimes reveals patterns no single team would notice alone. What happens next depends partly on what 3i Atlas does in these coming weeks, but it depends more on what we do, whether we treat this visitor as just another comet to catalogue and move on from, or whether we recognise it as an opportunity, rare, fleeting, and potentially transformative, to learn something fundamental about what exists in the space between stars, the explosive brightening, the missing dust, the radiation crust, the precise timing, the high mass and structural integrity, the flat trajectory and extreme age. Each of these alone might be explainable, but together they form a pattern, and patterns are what we should pay attention to. Maybe the pattern resolves into a natural explanation we just haven't thought of yet. Some combination of composition and history that produces exactly these characteristics without requiring anything extraordinary. Or maybe the pattern is telling us something we need to hear. That interstellar space is more interesting than we imagined. That objects travelling between stars can be fundamentally different from anything in our local neighbourhood. That our categories and models need expansion. Either way, the answer won't come from dismissing anomalies. It will come from studying them carefully, from being willing to ask difficult questions and sit with uncertain answers, from following evidence rather than assumptions. 3I Atlas is still out there, still visible through professional telescopes, still releasing gas, still showing activity, still carrying its secrets through the solar system. For now, we can watch, we can measure, we can wonder. And maybe, if we're careful and thorough and honest about what we don't know, we'll learn something that changes how we see the universe, because that's what these visitors offer us. Not just data points and spectral lines, but chances to look beyond our expectations, to see that reality is larger and stranger than our models predict, to remember that we're still at the beginning of understanding what's out there in the cosmic dark. 3I Atlas came from that darkness, from depths of space and time we can barely comprehend. It travelled for billions of years, survived conditions that would destroy most objects, and arrived here just as we developed the technology to detect it. For a brief moment, it blazed bright enough for us to notice, bright enough to study, bright enough to raise questions that will outlast the comet itself. And now it's leaving, moving back into the darkness, carrying with it whatever answers we failed to extract in the time we had. But the questions remain, hanging in the space it's leaving behind, waiting for the next visitor, the next ancient traveller that will drift in from the void and challenge us to look more carefully, think more deeply, question more honestly. The universe is speaking to us through these objects, through their chemistry and their trajectories and their inexplicable behaviours, through the gaps in our understanding and the patterns we can't quite explain. Are we listening carefully enough to hear what it's saying? That's the question 3I Atlas leaves us with, not whether it was a comet or something else, but whether we're ready to truly observe what the universe shows us, even when it doesn't match what we expected to see. The data is there. The observations have been made. The anomalies documented. What we do with that information, how seriously we take it, how thoroughly we analyse it, how open we are to following it wherever it leads, that's up to us. 3I Atlas is moving away, but its legacy is just beginning, in the papers that will be written, in the debates that will unfold, in the missions that will be planned to intercept future visitors before they slip away, and in the reminder that the cosmos is full of mysteries, that some of those mysteries pass right through our solar system, close enough to touch, and that if we want to understand them, we need to watch carefully, question deeply, and remain open to possibilities we haven't imagined yet. The ancient visitor came, performed its impossible dance, and is now departing. What it taught us is still unfolding, and what it asked of us, to look beyond assumptions, to question what we think we know, to remain curious even in uncertainty, that lesson remains long after the object itself has faded from view. Sleep well. Dream of ancient ice and billion-year journeys, and know that somewhere in the darkness beyond our solar system, other visitors are already on their way. What they'll teach us when they arrive, we can't yet know, but we'll be watching.